It's got recording at the top. Looks like it's
good.
recording.
Yes.
Oh, and I can see sound waves going because it's picking up me talking to it.
Okay, so this second half, okay, we're looking at the whys and the wheres and hows and approach, which I've done to improve this reliability, the gait reliability. Okay, joint rotations. Again, there's a couple of things at the beginning to get through, just some understanding of a few things before we flow into it. Okay, joint rotations, they're described as a rotation about the x-axis, the y, and then the z. So look at this. This is my kind of diagram. It's quite hard to represent in one figure all the stuff's going on. But we have x, y, and z is rotation in the plane of this screen around about the x, then about the y, and then finally around the z. So the blue, then the green, and then the purple to get from x, y, z to x, y, z. So there's three ordered rotations basically, and so joint angles calculated depend on calculating those rotation about x, rotation about y, rotation about z. And the rotation order in matrix terms is the reverse order than which you read. So it's x times the y times the z. It's just backwards. Rotation x, rotation y, rotation z. So those doing the biomechanics and done this before will see that. Oh yeah, I recognise that. So x is your flexion extension axis, y your abduction axis, and the z, in this case, internal external rotation axis. So go x, y, and z. Okay. As we can see, if you multiply all those three matrices out, there's three of them, x, y, z, you end up with a large set of nonlinear equations that you can solve to actually calculate what those x and y, what the rotations are that relate our two axes together, that relate one axis to the other. Okay, this is where we need to understand what's going on. Nonlinear area. It's a misalignment between segment axes. Okay, a misalignment between the true axis of rotation. So if I'm going like this, we've got a true axis, my hand's just going from there to there and back up again, flexion extension, more or less. Okay, if we have a misalignment of axes that we're doing our rotations around, something else is going on. Instead of going from here, start to finish, so here's our start, that cube up there has been rotated and gone straight down here, so red there, now it's on here, the blue is now underneath and the yellow stays on this side. So it's just a straight rotation about an x-axis here, purple. Okay, the misalignment of that just means that instead of rotating about this axis, we're rotating about another axis that's twisted, in this case like 45 degrees. So instead of getting from there to there, we've still got to get from the same position to the same position. But in doing it, we're describing it by a rotation out of the plane over here. But to get to there, we've got to introduce now an abduction rotation. So instead of going straight down to here, we've had a misalignment of axes that we're actually describing our rotations about, that are not the anatomical rotations, and we've hit it out here. Okay, we've hit it out, it's sitting up on its corner now. It's gone this way, 45 degrees, hit it out here. To get back to this position, we've got to introduce an abduction, bring it back to this point, and then we've got to introduce a rotation to get it to where we want to be. So to think of it anatomically, we go from here to here. Okay? But our rotation that we're defining is actually heading over here, introducing our abduction to bring it around, then introducing a rotation to straighten it back up again. So that is misalignment error in a nutshell. And with axis misalignment, we're heading somewhere where we're not intending to go. We have to introduce rotations to bring us back to the alignment that we need. While anatomically, the segment has just gone from there to there. Okay? But the axes that we're using are not aligned with the true axes of rotation. Okay, and that introduces errors. Okay, in the literature, it's been it's not been well documented, but it's been documented for quite some period of time. It's commonly called crosstalk, and you've got people like Allan back in 1990 described with knee flexion extension, abducted action, saying that okay, if our axes aren't aligned, we get this crosstalk, and it's going to affect our abduction adduction into external rotations. Baker, he said something like that the crosstalk it can be sufficient to make our internal, external, non-sagittal plane rotations meaningless. They can be overwhelmed by crosstalk. And Gross, 2005, went along the lines that saying that you cannot draw conclusions on your data or valid conclusions unless you've tested and checked to see that your non-sagittal rotations have not been affected by crosstalk. So this has always been there in the literature. It's been described, it's been talked about, but it's not been fully understood. They were all correct, but they probably didn't realise about how correct they were and how big an effect it has on the rotations that you calculate compared to that real actual rotations. So probably not fully understood, not fully developed, as ideas, as concepts. Right. Now, I'm going to try and explain this easily. If you don't understand it, well, that's fine. Right. So this is rotations as we saw the previous example, as it's expressed. A rotation of measurement x, y, z. But they are not calculating the true rotation. The true rotation has a little bar on it. So that's not the true rotations. What they're actually measuring is a rotation plus an error. Okay, so there's an error in the x, an error in the y, and an error in the z. Okay? This is what they're actually measuring, putting the error in. And so this form is probably recognisable from the research. You have the real plus an error gets the measured. Okay? This is the measured over here. Okay? There's a real rotation in there. There's an error in x, y, and z, the real rotation, and then there's an error post x, y, and z. The real plus the error giving you what is actually measured. What is measured is the real plus an error. So this is actually what it's actually measuring. Okay, this error is an error in the proximal segment, a pre-error, an error in the proximal segment alignment. So in that previous example, we had that cube up there, it was twisted and went that way. So an error in the proximal x, y, or z alignment, and an error in the distal segment x, y, z alignment. Okay. If we skip down here, and so this is how it's been used in the present study and in the research that I'm presenting. We've just rearranged this and looking at it from another perspective. We've got the error rotation. This is what's being measured, as presented in all the studies previously. This is what's measured. Instead of an error, we're going to talk about a correction. A correction in the proximal axis, x, y, z, to get the proximal axis where it should be, then the error rotation, and then a correction in the distal axis to where the distal axis alignment should be to get the real value. So this one just rearranged. This was a real plus an error, guess what's measured. This is what's measured plus a correction gets the real. Okay? So it's just a different way of looking at it. Right. I am trying to get, I can't kind of go through the whole thing in one session, but to try and understand it, the correction and the error. Okay, so I'm using this one here. We've got this one, we've got an error, and we have, so what's measured is this. What's measured, that corresponds to that one, x, y, and z. That's what's measured. So that's the real plus the error. The correction in this case is to the proximal segment. The correction is, well, this was the error, a 45-degree twist here in our x-axis, pointing back that way. So that was the error. So our correction would be minus 45 in here. That will stay as unity, the unity 1, and that stays as it is. So what happens is, from the erroneous rotations, you can put in the correction and get the real rotation, which will just be over here, that single x-axis rotation. So it's a way of getting from an erroneous measures, putting in corrections, so that's actually alignments of our axes, both from our relatively proximal and distal segment, XYZ axis, the correction needed to recalculate the rotations to get the correct, which is just an x. So that's how nonlinear error and how it is corrected in the studies. It's looked at by a correction, from what's calculated, it's looked at a correction to the proximal or distal segment alignment and what effect that has on the calculated rotation. Okay. There were 3 matrices there that you multiply together and we end up with that big matrices you saw earlier. We ended up with, where did we go? Ah, that one. Okay, that was for 3. In this case, you have 9 matrices that you are multiplying together. This is huge. Okay? The equations are big, they're highly nonlinear, but they can be determined, multiplied out. Be very careful with your sines and cosines and everything else. Where are we up to? But it can be multiplied out and can be worked with to correct rotations. So it's a very big, highly nonlinear system. Okay. Moving right along. Okay, we better apply this. So we're going to apply it. So we've got a test case. One subject analysed 3 times. Well, one subject, they were only tested once, but they were analysed 3 times. Okay? But in the static pose, when you find your axes, one was initially aligned best can with segment axes, flexion extension axes, then the thigh, and then the next thigh was externally rotated, so the knee axis externally rotated 10 degrees, not externally rotated 10 degrees, and internally rotated 10 degrees. Same data analysed, but with 3 static poses. One with the thigh, the medial lateral of the knee, aligned as best as you could with where it should be, and then twisted one way and then twisted another. So an error was introduced, okay? The plus and minus 10 degrees. Same analysed, same trial, analysed 3 times. Okay, so here it is. Hasn't affected hip, flexion extension and adduction. We've twisted the knee rotation when we analyse it. And here we see hip, internal, external rotation. Plus 10, minus 10. Okay, there's the original, they have changed. The original is through here, offset of the thigh. Plus 10, minus 10. Knee, it has affected the knee. If you zoomed in on there, you can see some variations in the knee. It's affected, instead of going there, we've gone out this way and then come around, or that way and then come back and then another twist. It has affected the knee, but only very small, quite, hard to see. But it has affected the calculated knee abduction, adduction, internal, external rotations. That's the correction to come back in and the correction with the actual rotation. And it's produced some characteristic offsets by that axis misalignment. So the next thing to do, we knew the error that we put in. We have that equation that we went through before. We put in the correction, the negatives. So instead of plus 10, we put in minus 10. Instead of minus 10, we put in plus 10 to the respective data. This is after it's calculated. We're not going back to the original, back to the static and aligning our axes back up again and recalculating. We're just working with the calculated joint rotation data that is in error. Rotation data that has error in it. And applying the correction. When you apply the correction, we're back here where we should be. Okay? This drops back down, this drops back down, these drop back to our original, where we had our thigh segment, our medial x-axis, flexion extension axis of the knee aligned best we could. It drops back to where we expected it to be. So we can correct, again using the face, we can correct erroneous data by putting a correction factor to get a new set of rotations, and we want that new set of rotations to be closer to the real values, which is going to be the next thing. What are the real values? Okay. Okay, so that's this example, nonlinear correction. Okay. Let's have a look. Here's one I just did. Erroneous data, we fed in the error, then post hoc corrected, knowing what the error was. Okay? We corrected on the proximal segment, the actual rotation of the proximal segment, which fixed the nonlinear errors that were calculated for the knee joint rotation, which is the rotation between the proximal and the distal segment. Here, this is some data that was presented in the literature. You look at it and you can immediately see, or should I immediately say, yeah, I can see exactly what's going on there. Okay? Externally rotated, almost identical to what was in here, and saying, externally rotated thigh, and almost identical thing going on here. And this one, slightly externally rotated. I've got that around the right way, we didn't do it. But anyway, it's slightly towards this way, slightly external rotated. Come up with some values, approximate values, what the correction should be, feed into the formula, it spits out a corrected knee joint rotation. Didn't quite come ideal, you know, it didn't all converge on one line, this one did, but it did remove the error to see what's going on, and it approximated more closely what was going on here. So the thing is, experimental data, you can see it, you can recognise internal and external rotation patterns, characteristic patterns, and they can be corrected with an actual, in this case, axial rotation. There's more going on here. The axis misalignment, though, is a function of, it's not only just where you've defined the axes, where it's misaligned, but during the movement as well. There's skin movement artifact, which adds to it. So you've got an initial misalignment, then skin movement artifacts then add to that as well. So there's more going on here, and maybe there's a deeper investigation on correction and having, instead of just an offset, need some dynamic offset as well related to skin movement or something there, or the angle or something. But let's see what's happening.
Sorry, this may be a completely stupid question, but in reality, how do you know how much offset you've got to correct for?
Well, I've got to find out what the real one is. But we're coming to that.
But you had to go at someone else's data just there.
Yeah, trying to get
Did you just go through a process of trial and error?
Yes.
Right. Yeah.
We're trying to, okay, I look at this, okay, that's externally rotated, almost the same as here, around 10 degrees, that's the other way, 10 degrees, and that slightly externally rotated, maybe only 5 or a few less. Okay, we'll start with that as this, but plug that in, and then just, yeah, it was just a matter of manipulation. We're trying to get these as close as we could to being identical based on this. I should converge somewhere in the middle. So you have the, okay, so this is in the back of your mind here when you're doing this, but you're trying to converge this, get something identical. Yeah. Didn't quite become identical, but then there might be more going on with the nonlinear area. There's skin artifact and other dynamic things might be going on during the gait cycle, which is adding to error. Anyway, so, but this is more interesting. Well, it's another step along the way. But going back to the original data, okay, knee flexion extension. Each of these, the mean of 10 studies presenting normal joint motion. Yep, knee joint motion. Abduction, adduction, internal external rotation. Same thing was done. You look at this, particularly the internal external rotation. You look at the proximal segment and the distal segment, and you look at, okay, if we take the erroneous data, so the calculated joint angles plus the Lagranges. We have a correction in the proximal and distal segments, we then produce a corrected value. That corrected value we want to be, we would like it to be, the real value of the rotation. We play around with it, we get some data in, try some corrections, and that's what I ended up with. That's the best I could do at getting some kind of convergence with the data, just using nonlinear correction, post hoc, after the fact correction. That is not ideal, doing it that way, but you can see that we have produced something that these characteristic curves, or common, more common, they're not quite so common. Again, we look at stance, swing, swing has a bit more going on. But we've produced underneath all this, if we correct the data, we're looking at it from the perspective of an error in the proximal or distal alignment and all the non-linear effects that has on all the calculated rotations that come after it or before it, if you're looking at the proximal or distal. Then underneath that, there is, and what I'm not saying is, a common knee joint kinematics, a common knee joint flexion, abduction, adduction, or internal, external rotation pattern. Common to all of these, hidden by nonlinear error. Okay. You cannot, if you have an error like we saw in the flexion extension here, oh geez, I've messed up there a bit. I'll just add an offset and correct that. You know your alignment, and you look at your hip, internal, external rotation. We'll just fix that up. You cannot add or subtract offsets to rotations linearly, just like you would numbers or axes. You know, you go along X, you add a bit more on the X, you go on the Y, you add a bit more on the Y or Z, or you know, you can add or subtract there because they're independent. These aren't. You cannot have an offset for any joint rotation and just say, I'll put a correction on here. Same thing, you cannot take a static trial, calculate static joint angles or movement joint angles and look at the static and say, oh, there's an offset there, I'll just add or subtract an offset to my calculated rotations. That is incorrect. It is wrong. You can't do it. It ignores the whole nonlinear nature and interrelation and dependence of calculated rotations on the alignments of the proximal and distal segment. If you change one, you're going to affect rotations that have been calculated at other joints. So thigh, you change that, you're going to change hip and knee rotations. Okay, if you change the shank orientation, you're going to change the knee and the ankle rotations. And it's not just one, it's the whole lot in a big nonlinear fashion. So you cannot simply add or subtract joint angles as if they're independent things and you can just add and subtract values from calculated joint angles. You've got to go back and view at it as correcting proximal distal segment alignments and account for the nonlinear nature of rotations and how they are affected by these changes. So that's a major point there. That correcting this and also correct this. We just looked at a simple example with one offset about the proximal segment being rotated slightly, plus or minus 10 degrees. But you've got proximal segment rotated about all three axes as an offset, and a distal segment errors about all three axes, and correcting the whole lot in a big nonlinear fashion. Okay. Okay, the other thing that comes out of this normal gait rotation between studies. This is the first time ever that a normal knee joint kinematics, abduction, adduction, flexion extension, flexion extension is okay, that's sitting over here. Abduction, adduction, and internal external rotation have been presented, or at least justified. Okay? I could say, okay, this is a normal knee joint kinematics. And there's going to be some debate on that, and there's some more research done, and you might find that, okay, this wasn't quite, it's actually slightly different. Might be some small variations in there. but it's the first time it's been presented a normal knee joint kinematics, non-statural plane rotation, which has some justification, has some evidence behind it. These again are normative data that I've corrected. Ideally, if you're doing post hoc correction, you wouldn't use a normative data. You would use individual trial data and do corrections on that and then calculate the norm. But I do 10 average patterns of normal, or 10 studies. So I've used average patterns and did post hoc correction on an average of a whole lot of gait cycles that were in error. So I've done correction on the average rather than the individual. So ideally you do it on the individual rather than the average. But anyway, it's been done and we've got a normal, or what I expect is a normal knee joint kinematics. Okay, so we've got to a reliability study. So we're going to make use of all this that we've looked at so far. Participants, 11 healthy subjects, mix of male and female, 12 camera motion analysis system, fairly standard, or these days it is. The segment model, I'm not going to go into it in any great detail. These pretty well describe it. 7-segment marker cluster design, virtual joint centres. There's virtual joint centre hip, knee and ankle, which are included in the clusters. 6 degree of freedom, so each joint is allowed to move, and a least squares approach. That pretty well sums up in a few words the design. So 7-segment marker cluster, virtual joint centres, 6 degree of freedom, least squares. The pelvic, yeah, pretty standard, okay. A cluster of markers in the pelvic, pelvis. Thigh, there's a cluster here, including the lateral knee and the virtual hip joint centre that go into make the thigh. The shank, with a cluster around here, plus the ankle, plus the virtual knee joint centre, which go into making up the lower leg. And the foot has a cluster around here, plus the virtual ankle joint centre, which go into reconstruct the foot. So there's nothing out of the ordinary there. It's a cluster design. Protocol. Each participant underwent 6 gait assessments. Okay, so 6. Me as experienced examiner, I was experienced one. I tested each participant on 3 separate days over a 1-week period, and there were 3 other examiners. They were 4th year physiotherapy students for the novice. They had 1 afternoon training in all this stuff. That was it, and then they were let loose. But being 4th year physiotherapy, they were familiar with anthropometry and skin folds and taking measurements, and so they were comfortable enough doing it. And so they all tested each participant once each as well on separate days. So there were six gait sessions that every participant went to. I always did the first session out of convenience because first time they came in, they had the protocol and procedure, had to be explained to them what's going on, informed consent, do that kind of stuff. So I always went first on the first session, but randomised after that. It was not particularly complicated. The first session that I took generally took 35 to 40 minutes to do the whole gait session. Subsequent gait sessions were only 20 to 25 minutes to do, where you didn't have to worry about the informed consent and all the stuff to start with. They came in, they knew what was going on, and just get straight into it. So 20 to 25 minutes for the gait assessment, collect the data, and also not included in here was part of it, also collected skin folds. It's not included here. So in that 20 to 25 minutes was also 6 sites on the lower limb skin folds, 3 sites each. So that chewed up probably about 5 minutes, about 20 minutes. So reasonably quick, in and out, and not very complicated. Test procedure, height, weight, marker placement, so put the markers on, record a standing pose, okay. While they're standing there, so you capture a second or 2 of them standing, then measure. Knee flexion angle, okay, so you measure at this angle. Hip abduction angle, okay, it's measured from behind, but hip abduction angle, foot progression angle, and rear foot angle, so pronation, supination. These were just simply done with a goniometer by the individual, a long-handled goniometer lining up with a segment. Okay, I'll say later that is one of the, there's a little bit of a limitation, but it got us a good approximation of those standing joint angles. We removed the medial markers of your knees and the ankles and did your walk trials. So 6 to 8 walk trials, and from each trial you get a few gait cycles, so you end up somewhere around 10 to 12 gait cycles. Bare feet, own pace, and it's about a 7.5 metre walkway that was being recorded. They came in, went through it, then went off and came back. I'm just going to add this because that was the way it was done in the reliability study. Since then, and with the CPQs and various other things, I've introduced a squat movement before and after movement as well. So you've still got everything else the same, but you've got a squat, so just doing like this before, they do whatever they're going to do, and a little squat after they're finished, and then finish. So a couple of things have been added in. They weren't part of the reliability study, but the things that I've added in kind of since then. Is just a squat movement before and after, whatever the movement trial is. Analysis, we're going to go through this really quick. So all examiners, all the group of us, we all did the post-processing. It's just like, okay, we just divvy it all up, there's a heap to do. And so it wasn't just one person doing it, it was a whole mixture of doing the whole lot. So the thing you do is just correct the motion analysis system. You make a template and it auto-IDs as you go, but that needs a bit of correcting. So there was correcting identification of markers. There was limited filling of joints or gaps. It was only if you're like 10 frames or less, you've got a little gaps, they would be filled. Anything larger would leave. Okay, so limited filling of gaps. There was no smoothing of raw 3D data, and that's important. Okay? No smoothing of raw data. A least squares construction of segments, so you have your 6 marks per segment, and your virtual joint centre. Least squares reconstruction. Every frame, okay, so this is part of the reconstruction algorithm. For every frame, the RMS area is calculated between the local coordinates in your static pose and the global coordinates in your movement trial. So the least squares fit from one onto the other. And you're working at the RMS area of that. And that was screened for all reconstructed segments across all trials. So what I have to compare that with is some criterion values for the RMS error for each segment. So for a perfectly identified, tracked, labelled trial, we know what the mean and the maximum, so mean plus 3 standard deviations of the RMS error should be. Okay? For each segment. It's different for each segment, just depending on just the amount of stimulant artifact and other things that are going on. So I've got these criterion values. This goes through, everyone is compared to that. If it's over the limit, that frame on that trial is an error. There's something going on. It's larger than expected values. We'll go back to that trial, that frame, and have a look. It could be a marker has been misidentified. It could be you get things like ghost markers that have been reconstructed from cameras and reconstructed a marker that doesn't actually really exist. Those camera rays actually belong to another marker that's been misconstructed, and some rays have intersected, and you get phantom markers floating around. It may have jumped to a phantom marker, or it may be the marker was visible in 3 cameras, it dropped to 2 cameras and there was a jump. Came back into 3 cameras again and there was a jump back to where it should be. Things like that can be automatically picked up, identified and eliminated. So that marker, that point can be corrected or removed for those frames using the RMS error. So there was screening of all the data using the RMS error of the reconstructed coordinates in the data trial relative to the local coordinates of those markers in the static trial. So fit one onto the other. Joint angles calculated, heel strikes and toe off are manually identified for every trial. That's a mission. Okay, using X, Y, the heel toe coordinates, go through every trial, heel strike toe off, and then gait cycles extracted and all normalised to 100 frames. So that's the analysis procedure. Okay, the axis alignment. This is kind of in the heart of it. there is an initial estimate of axis alignment. This is in the standing trial. So, in the standing trial, weight bearing extended knees, it is assumed that the proximal, that the knee abduction, adduction, internal, external rotation is 0. Okay, so flexion extension can vary, but abduction, adduction, internal, external rotation, extended knee, weight bearing is going to be assumed here is 0. Then the axes fit, pelvis to the thigh, shank, foot, are fitted with that constraint to best fit those measured joint angles. So the knee flexion extension, the hip abduction, the foot progression angle, and the rear foot angle. So best fit those while keeping the abduction adduction 0. That's our initial estimate. Okay, then what was done in it's our first refinement. So what this is one walking trial was taken and analysed. We look at the differences between calculated knee non-sagittal rotations and those normal values that we saw earlier. The ones I said, we've got normal knee joint rotations, non-sagittal plane, abduction, adduction, internal, external rotation. So we analyse the walk trial, we pull one out, we analyse it and look at those rotations. And we go back to the static trial, minimising differences between our measured, keeping 0 internal, external knee rotation, but also now trying to reduce differences between that normal pattern of walking, knee, internal, external, abduction, adduction, internal, external rotation, and what we're getting. So there's a little second refinement, first refinement, initial estimate, first refinement of axis alignment. In subsequent trial, now since this study, I said, I added in the squat before and after the movement. They come in here and are used as something independent, okay? Especially with CP kids, where you haven't got a normal thing. So with the CP kids, we haven't got a normal thing to work with. You've got a squat though, before and after, just something like this, and we're just trying to minimise the range of motion of the abduction, adduction, and internal, external rotation. But we've got initial, first refinement. Then the second refinement is the post hoc. Now, hopefully, if you've done the first two well, the second refinement, which is done on a trial-by-trial basis, is looking at the results, trial-by-trial, looking at the knee abduction, internal, external rotation, looking at our normal values that we saw earlier, and do they agree? Are they in agreement? Don't have to be exact, but are they agreeing? Again, it's subjective. It's following closely what we would expect from normal walking of healthy adults walking up and down. So there is a second refinement, which is a post hoc correction. Now, hopefully, as I said, this post hoc correction is small. We're only talking a degree adjustment here or there to minimise those differences. So that's axis alignment, three-stage process. Statistics, outcome measures. We've got inter-session, okay, 8 to 12 gait cycles. But inter-session, there were 3 sessions, that's me, 1, 2, 3 times. We have an inter-examiner, there's 4 examiners, me and 3 other novice. And so that's that. Statistics again. Average standard deviation. The correlation measures, CMC and ICC were calculated, but they're basically ignored now. We're just going to stick with average standard deviation. And same thing as before, we have, what are we looking at? Knee. We're looking at flexion extension, knee, hip, and ankle. We've got similar, identical, similar, different, unrelated. Again, there are some variations in here, there's some subjectivity in there, as to where those borders are. And we've got a minimum clinically important difference based on 95% confidence interval and a minimum clinically important difference based upon standard deviation. For the intra-session, this first column, we're looking at this one. Intra-session, you have a collection of data points, collection of data, intervention, collection of data, but they're all under the same conditions. So we're looking at 95% confidence interval, looking at this value. So they're all well under where we'd like to be. For the inter-session, you're looking at the minimum clinically important difference based on the standard deviation, because typically you look at we have one session, they go away, come back, some days later, and you do another session. You know, single value. So we're more interested in this is below this value for the inter-session. Then there's the inter-examiner as well. And then this one is the total variability. If we just plonk all 12 subjects together, so these reliabilities are intra-subject, within a subject under same conditions or the same examiner or different examiners, but within a subject. This is just all subjects. Okay, so within subjects here, all subjects, the total variability across all subjects. So you can see, as a group of subjects, they were quite different. Well, different to unrelated as individuals. So there's quite a bit of variability in their movement patterns. But within a subject, they were quite tight. The hip flexion extension, all fine. But you see, inter-examiner, it's creeped up a little bit. Okay? We'd want to below here, we'd want to below there, but it's crept up a little bit. So some work needs to be done into examiner reliability. You want to pull it down below this line. That's again assuming single measure, one examiner, single measure of another examiner. We have multiple tests, one examiner, multiple tests of another examiner, so different days, and different days again. Then you could use the standard deviation you'd be thinking of here. Okay, so multiple measures, multiple sessions, or single session. Okay.
Now, all subjects, that's variability between subjects. That's subjects varying between each other in the gait cycle.
Yes.
Does that, and again I may have this completely wrong, but does that have any implication on the kind of model that you're using, where you expect you're looking for similarity of cycles when you set these criteria for reliability? Because that's suggesting to me that there is some variability between people. So when you're looking for similarity of gait cycles, you've got to take into account that there is some variability.
Yes.
Is that a consideration, or am I completely out of the ballpark?
That's fine. Yeah, that's fine. Yep. So with the knee flexion extension, and we'll see it later when we're talking about the knee non-sagittal ones, which was our ones we were trying to minimise, that there is differences between individuals. You would look at them, set up 10 individuals walking up and down, and you look at them and say, yeah, these are different. But in the methods, you've got this underlying normal pattern. Now there is assumptions here in this, that this is a normal pattern of what you'd expect for a normal, healthy, walking up and down individual. And you're trying to minimise differences to that pattern to try and reduce that non-linear error, or as is often termed crosstalk. So you've got that as an overriding that pattern there that you're trying to match with your non-sagittal knee rotations. But still, we might as well have a look. Abduction knee, they are still different, and of the knee. They're still regarded as different than one another. But we're trying to reduce that non-linear area, the axis misalignment, based on an underlying assumption that there is a common or close to a common pattern there that they should be around. Not exact though.
No.
It's not an exact fit, but you're trying to minimise towards this, because there is considerable variation between subjects.
Well, and what's the general view of people who write about gait is that gait variation between people should be quite minimal? Is that the general feeling of the field? Does that make sense? So the variability of gait between people of a similar age is assumed to be reasonably minimal.
That's all relative, isn't it? I mean here we're just talking about intercession and the same individual on repeated days. Here we're talking between individuals. Relative to that, it's large. So I suppose it's relative, isn't it? Yeah. Yeah, that's a
Don't worry, keep going.
yeah. But I suppose walking compared to running or to other movements, you're saying it's small. Yeah. So it's kind of a relative thing. Again, okay, we've gone on to abduction adduction. Here we're fine. Fine. Again, this is fine. Inter-session, intra-session, inter-examiner. Again, slightly high again. Something to look at here with inter-examiner. What was influencing inter-examiner? Maybe the goniometer stuff at the beginning. Something to really look at. It's not an ideal, looking back on it, it's not the ideal thing to use the goniometer like that. Maybe something we need to do there is have 2 examiners doing goniometer, one to measure, one to check. As a check on the first, if that initial alignment of axes before you start trying to minimise and reduce differences to a standard or an expected value on your knee non-sexual rotations. So maybe there's a need to look at that initial estimate, the goniometer, and to improve between examiner initial estimates, have 2 examiners there. One, as I said, one to measure, one to check, or one to verify, to help reduce some variability there. So there's some things there to look at in inter-examiner. So we'll keep.
I was just wondering, just so again, so that do those differences, which obviously they're all again on your criteria, some of them are outside the green, but they're still less than a degree, and so they look quite small.
Yes.
And then I wonder, does that have any effect on the moment at the joint, which is probably the thing that influences the injury risk or whatever anyway? Is that a consideration?
Okay. These are small.
Yeah.
In here, we're talking about small little changes. The whole 2 things I'll say. These are putting a line down, and that's okay. Here's a criteria. We've got, so this is what we're trying to achieve. Are we there or are we not?
Yep.
Okay, so the first time there's a line you're saying this is where you want to be, and there or you're not. Okay, we're not quite there, we need to get better. But they are small changes. There's subtle differences there. But if you stick a line and you're saying, no, it's not there. We're not quite there.
In your experience, do you think that those changes would change function?
Yeah, now moments, I can't say with moments how big an effect that's going to have in moments. They're little, they're small changes in pattern. I can't say for now how big an effect that's going to have on moments. But what I can say is with the previous data, we saw look out here, different, way out here, unrelated, and that the very first plot I put up of knee internal external rotations and I had all the unrelated patterns.
Yeah.
That will affect moments.
Yeah.
Because if your axes are out of alignment, that shows up in your rotations. And you can use the rotations to correct axis alignment. Okay? So that's basically what I'm doing. But if your axes are out and you're calculating moments, you are calculating moments about those axes. So what is your flexion extension moment? What is your internal external rotation moment? What is your abduction moment? If those axes are out, then your moments are going to be out. You've got what's been termed crosstalk going on. Okay? So in the previous methods, yes, your moments are out. If your axes are out, it'll show up in your rotations. If your axes are out, it'll mean your partitioning of moments into these planes is also out. And we've seen this large variation in this axis alignments and large variations in the angles that are being calculated. And therefore there's large variations and inaccuracies in the moments that are calculated because your axes aren't correct. So previously here, it does affect moments. You cannot ignore bad rotation angles and say, oh, my moments will be okay. They won't. Then on here, at this level, we know how much it affects moments, and we're talking subtle differences in alignment here to get from here to here. I don't know, a degree or two or something, but maybe it won't have a great effect for moments. Maybe if you're down in this area, that's fine for moments. Okay, we'll just get along. How are we going? We're going to keep moving. Okay, least varied across all participants, as expected, fit and knee, abduction, adduction. Most varied was knee internal external rotation. This is probably something new. Oh, there is something else. Okay, here it is. Intercession. This is unique to this study. No other study's done this. Intra-session variable, besides being a lot smaller, every other study, intra-session, reliability. You go to inter-session, there's usually a jump, a big jump, poor reliability. Inter-subject, another big jump, poor reliability. This one, the only reliability study I've seen, intra-session, you go to inter-session and there is a consistent drop, an increase in reliability. You're more reliable for the same subject testing on different days than on the same day. That's all angles except for the one, this one here, that's the only one, the knee adduction was a slight decrease. But every other one, there was an increase. And normally it's a big decrease, another big decrease. Going intra-session, inter-session, inter-exam. Why this is? Well, part of the reason is the nonlinear error and all their rotations are confounded and completely overwhelmed by nonlinear error. But why this is better is you walk up and down, you've got individual trials. So subtle variations in speed, in step length, step width that come in to produce variability walking up and down. Yeah? You take the mean of that trial, okay? And then you come in another day, you've got subtle variations in walking speed and step length and step width, and so there's variability there, but then you take the mean. And now inter-session, you're comparing mean and mean on a third day. That has reduced or increased the reliability. It's reduced the variability between sessions, and that's why it's dropped. Okay, what we're going to have a quick look at, now this was very relevant to what Kelly was talking before about stance and swing. This is the overall results of 10 participants put down, okay? This is just the whole 10, what it looks like. Knee, hip, flexion extension, hip adduction, hip internal external rotation, whole 10. And this is the between participant variability here. There's something interesting in here. There's a group which are lower flexion or a group of higher flexion, and there's a group in the middle. But you actually start to see, if you get reliable data, some patterns going on here. Now there's only 10 subjects, so it's very speculative. You'd have to do this again and maybe a whole lot more subjects to see whether this occurred, on a consistent basis. But there is some patterns here, and you see it here in abduction adduction of the hip and in the internal external rotation. There's a group of increased and decreased. The red line is the median. So there's a group on the median, purple on the median, purple on the median, and a group above and a group below. Group above and a group below. And slightly visible here as well. The median and a group above and below. And above and below. There would appear to be some variations within the individuals into some subcategories or types of patterns at the hip. Okay, and if we look at the knee, that was just putting that up, that was just comparison, the whole lot. Mean of 10 after correction and my 10 here. The knee, the same thing's going on. We seem to have groups here. There's the mean, the red. We have a group below, a group above. Increased, reduced flexion, and same here. And it shows up in abduction adduction as well, and internal external rotation. Above and below the mean. So there appears to be, within walking, even though you've got some characteristic patterns, some division, subdivisions within that of increased or decreased flexion extension, abduction adduction, or internal external rotation. So some patterns within it. Again, it's speculative. It's just something which noticed when analysing the data. And ankle, again, not so obvious in ankle, but there is some separation above and below the mean. Not quite so obvious in the ankle. But this is what you're talking about here. Within subject, stance, swing. The highest variability, relative variability, if we go back to the results, was in knee external internal rotation. That primarily comes around stance. So this is relative. If you look at the criterion values and similar different unrelated paths, the biggest variability between subjects is knee internal external rotation, and that is here, the swing phase. So there's some distinct variation in internal external rotation of as the lower leg goes between 5 as they come through, so internally or externally rotating. And that was the biggest variability, relative variability of all the measures. The least variable was this one, the knee abduction adduction. Even though you can see that there's differences between the stance phase and the swing phase. And if you just look at the swing phase, we almost look at identical, or very similar, but not identical, but similar gait patterns. Here we're looking different, here we're looking similar. Okay, so we're just going to touch on, probably 5 minutes left, I'm going to touch on some overviews, some thoughts to finish up. Okay. We need to address key factors of reliability. Now, I've presented this probably in a different way than it's ever been presented before. I'm coming from a different perspective. I've got axis misalignment over this side, and I've got quality of 3D data on this side. That's two separate parts, like pre-process or pre-data and post-data stuff, kind of separate. So quality of 3D marker protection. The two, and the axis misalignment, the two big things affecting reliability. We've got 3D marker coordinates, so that's basically your cameras, your calibration, your placement of cameras, number of markers, your 3D reconstruction algorithm. This, with modern systems, should be pretty good. The ability of a modern camera system to be able to reconstruct a marker, it's pretty good. But the errors are going to come in here, post-processing. So of this, the post-processing is the bigger factor. The tracking, the identification, the editing, the smoothing, everything you're doing with your data comes into that quality of data, quality of your 3D data. This stuff needs to be taken a very close look at, especially if you've seen these studies. Remember back to the literature review, intra-session reliability, getting different or unrelated gait patterns of someone walking up and down within a gait session. Same mark set, walking up and down, presenting results which represent unrelated gait patterns. We're really going to take a look at this. The other thing, axis misalignment, we've got the static definition that we've seen, so how you define your axis in a static pose, and then you've got the dynamic, which comes on top and adds to it. So you've got a static offset and a dynamic part, which goes with it as you're walking. So you've got a static offset and a dynamic. So your dynamic one, got mark error, just again your reconstruction stuff, getting markers visible in the 3 cameras and being reconstructed correctly, and then you've got skin movement artifacts, which go into the dynamic, which adds to the static to crack axis misalignment. So you've got to address these factors if you're going to do it. So standing position is a reference position from which anatomical rotations can be reasonably estimated or measured. It's not a 0 position, okay? But there is that assumption we're making about the knee, internal, external, abduction and adduction rotations, standing, weight bearing. So there is that one. But other than that, it's not a 0 position. And unavoidable consequences of relying on examiner. Examiner's judgment in placing of markers or using things like knee alignment devices or wands or whatever else is these mark errors. 2 of them. There's examiner error. I just get it wrong. I might get it right, and then I'm wrong. Or, placement could be right, and then an error, just one goes wrong. So there's that random error. There's also the examiner interpretation. So we're getting back to what I said right at the beginning. You've got to separate the model from the implementation. They're 2 different things. The implementation comes down to part of it is the setup and the cameras, but part of it is the model examiner's interpretation. So what they think they're supposed to be doing might be different from what someone else thinks they're supposed to be doing, or where they should be putting markers. So you've got the error and then you've got the interpretation. 3D markers should be constructed in 3 or more cameras. You can only use a marker constructed in 2 cameras if it does not affect that RMS error of reconstructed coordinates. and segments should always be constructed with 4 or more markers. Just to have a look at that. This is a quick plot. This is camera angle against error. 2 markers. 90 degrees, the error is minimum, 2 markers. As camera angle changes, the error increases to infinity. Okay? So marker error, 2 cameras, dependent on camera angle. So markers included in your model, in your least squares, should be from 3 cameras. If they're from 3 cameras in the least squares procedure, then it's not dependent on camera angle. If it's from 2 cameras, it is. There could be some large errors in that reconstructed point. We've got to screen it against RMS error, expected RMS error, that segment, to make sure it has not adversely affected the reconstruction or influenced the position. Then marker error in terms of cameras, it's 2 cameras, 3, 4, 5, 6, and 7 cameras. You're increasing cameras, you're getting slightly increases in. When they're very small values here, this is 1 millimetre, you're getting small increases. Markers per segment shows the same pattern. I haven't got a plot for it, but couldn't find it in time. But 3 markers per segment, certain error. 4 comes down, 5 comes down, 6 comes down, markers per segment. So there's a big increase from 3 to 4 markers per segment, and then small increases as we add in more and more markers. Beyond 5 or 6 markers, there's very little increase. What I've used is 6 markers on the methods we saw. Markers distributed well along 2 or more axes. That's been around for a while. I don't like that one, but I'd say do not use rigid plates or wands. They're all fixed together in a cluster on the surface, representing the motion of that surface rather than the underlying segment, and are not well distributed. Do not smooth raw data. Editing of 3D marker borders, so the cutting, joining, should be used sparingly. And you've got to screen all RMS errors when you reconstruct segment positions. Always model as a 6-degree joint. Right, we've finally got to here. We're getting very near the end. Not a big yellow one, not a highlight. If you're not assessing and then correcting or at least optimizing quality of 3D data, that was on one side, axis misalignment was on the other side, then you're wasting your time doing 3D motion analysis. Here we're talking 3D. 3D, we're interested in non-sagittal plane rotations. So if you're interested in non-sagittal plane rotations and you're not assessing, correcting, optimizing these, then you're wasting your time. If you're spending hours cleaning up data, getting rid of phantom markers that are floating around. You've got markers that a lot of your markers are only visible in 2 cameras. You're filling large gaps. Then do you expect to get reliable results? No. And then is your system good enough for what you want to do? So the number of markers, placement of markers, and the cameras and the calibration and the marker tracking. A modern system, yeah, it should be. If you've got a 10, 12 camera modern motion analysis system, the camera calibration, the quality here should be fine. The only thing that could be a bit iffy from one setup to another is the marker tracking and how well that's done. Finally, this is the last one. Think of this. Don't accept everything you're told. Okay? You've got to test it for yourself. People in research and in publications, there's a lot of stuff out there. Not a lot of good stuff. Even if it's recommended by a 3D motion analysis supplier, you look at Vicon, you look at motion analysis, you've got the Vicon's clinical gait marker set or Vicon clinical manager, that Vicon set for this. And motion analysis, you've got like Helen Haynes modified marker sets. You've got these are some of the original marker sets back in the 70s and 80s. They were outdated in the 70s and 80s. Those are outdated at least 20 years ago, but they're still here, even though they're terribly unreliable. There's only a few people, if any, that know what they're talking about when it comes to 3D motion analysis methods. So people come to you and they're advising use this marker set, use these variations of it. We've got to be sceptical based on what's in the literature and the reliability of those methods. So don't accept what's out there. You've got to test, got to analyse, got to critically think about the results of it coming out yourself. Okay? And what's going on. And that's it. Not. No, it's not the end. Well, it's the end of this presentation, but it's not the end. It's only the beginning. Okay? There's a lot more on this, on the whole reliability, markers, different movements. There's a lot more to come after this. So it's not the end. It's just only the beginning. It's presenting one perspective of it. Again, I said don't believe everything that's been said. Don't believe. Okay, that goes with what I've just said today. Okay, this is my thoughts, my perspective, what I found, my solutions, or where I think the errors are coming from, and how to go about correcting them. Take that, work with it. So it's not the end, it's just the beginning. Now, I will be giving a seminar later. It's going to be next year now, but on muscle modelling. No, it's going to be muscle modelling. That has the same problems. There are so many misconceptions, misunderstandings, poor methods in muscle modelling. And a lot of results that are just poor. That also, you need to go back to the foundations and start from the very beginning and look at going through the whole process. But that's for another day. That's it for now. That's it. All right, I'll get this.
Allan, basically the take-home message